Greetings, ladies and gentlemen. My name is Mandisa Ngcobo. I'm with my colleagues, Ms. Sangweni, Ms. Mungwana, Ms. Malati, and Mr. Mtunzi. We're here to present a manuscript under the topic that says the utilization of membrane technology to effectively remove microplastics and heavy metals from freshwater and wastewater. First, we're going to start with the definition of terms. Heavy metals are metals of relatively high density or of high relative atomic weight. Water pollution is the contamination of water bodies with a negative impact on their users, usually as a result of human activities. Microplastics are small plastic particles that originate from a variety of sources. So we have primary microplastics and secondary microplastics. Microplastics are increasingly recognized as important non-biodegradable contaminants in freshwater and wastewater systems, posing serious threats to human health and the aquatic ecosystem. Membrane technology is a separation process that utilizes selective barriers to separate components in a fluid mixture based on size, charge, or chemical properties. This technology is increasingly applied in water treatment, including the removal of contaminants such as microplastics and heavy metals from freshwater and wastewater.
Microplastic and heavy metal mostly affect humans and aquatic ecosystem. Ingestion of microplastic by marine organisms can lead to physical injuries and blockages in the digestive tract. Microplastic can absorb toxic chemicals from the surrounding water such as pesticides and heavy metals. When ingested, these contaminants can be released into the organism causing toxic effects. Microplastics have been found in human stool sample, and maybe you're wondering how can that happen? Well, microplastic can enter human food chain through seafood consumption, leading to potential health risk. Heavy metal like mercury, lead, and cadmium are highly toxic to fish and invertebrates. They can impair reproduction, growth, and behavior, leading to population declines. Exposure to heavy metal can disrupt essential physiological processes, including respiration, osmoregulation, and enzyme function. In human, exposure to heavy metal can lead to kidney damage, cancer, and reproductive issue.
As we now embark on the methodology of our research, I'll be telling you about the PVDF membrane and PVDF modified with CNOs. These membrane are an excellent choice to be used as method as they possess the ability to handle large volumes of water and consume very little energy, which then means that it can be used at an upper scale to provide more clean water to large volumes of people. Please take a look on the left hand side the illustration of the PVDF membrane. On the right hand side the filtration process using PVDF. As we can see, our process starts off at the very core of our problem, which is the presence of microplastics in our water reserves, and then moves on to the filtration of samples from our water reserves using PVDF and PVDF modified with CNO. And then this leads to the filtrate and microplastics being filtered out. And after being filtered out, they then categorized as heavy metals and microplastics. And after it being detected, they're then extracted from our water, and then we then verify this by ICPS analysis and reverse osmosis.
The findings on microplastics and heavy metals highlight significant environmental and health risks. Addressing these issues require improved waste management practices, effective water treatment technologies, and ongoing research into the impact of these pollutants on ecosystems and human health. Microplastics have been detected in various freshwater and marine environments, including rivers, lakes, and oceans. Studies indicate widespread distribution, even in remote areas. Research shows that ingestion of microplastics by marine organisms can lead to physical harm, such as internal injuries and reduced reproductive success. Microplastics have been identified in human stool samples, indicating human exposure through the food chain. Smaller microplastics, which are less than 130 micrometers, have been linked to immune responses and potential tissue translocation in humans. Heavy metals are also commonly found in wastewater and freshwater systems due to the industrial discharge, agricultural runoff, and urban pollution. High concentrations of metals like lead, zinc, cadmium, and mercury have been recorded in contaminated sites. Exposure to heavy metals can lead to various health issues in humans. It is found that neurotoxicity is caused by lead and mercury, kidney damaged by cadmium, and carcinogenic effects are caused by arsenic and chromium. Membrane technologies have shown effectiveness in reducing heavy metals concentration in treated water. These are the concentrations of heavy metals obtained by acid and water extraction of microplastics filtered from influent samples using PVDF membrane. The graph shows that magnesium had the highest concentration, copper had the second highest concentration, arsenic and zinc had high concentrations after 30 minutes extraction. This was during the extraction when deionized water was used. When acid extraction was used, copper had the highest concentration, followed by arsenic. Zinc was the third metal that had a high concentration. It was found that the maximum amount of zinc that should be present in drinking water is 5 milligrams per liter. Copper levels must be up to 1.3 milligrams per liter. And lastly, the levels of arsenic must be 0.01 milligrams per liter. High levels of zinc might show the existence of metal contamination. This graph shows the evaluation of the PVDF and PVDF or CNO's performance. The PVDF membrane that was purchased has a pore size of 0.45 micrometers and a porosity of 78%. The surface layer of nanoparticles, which are CNOs, that clog the membrane is the cause of the obtained porosity for the PVDF or CNO's membrane. Figure 2's flux study demonstrates that the PVDF membrane had a higher water flux than the PVDF or CNO's membrane because of its bigger pore size. Because CNOs are hydrophobic and have poor water solubility, only a tiny volume was filtered.
In conclusion, PVDF membrane successfully removed microplastics from wastewater and freshwater systems. The input microplastics were composed of high-density polyethylene, poly 1.4-butylene terephthalate, nylon 12, and cellulose. These microplastics were sourced from hotels, houses, schools, industries, and commercial businesses surrounding the treatment plant. High concentration of toxic heavy metals like arsenic, copper, and zinc were attached to the microplastics. The presence of microplastics and attached heavy metals suggests the need for improved wastewater treatment infrastructure. The research can be applied as a microplastic analytical monitoring protocol to ensure adherence to water quality and management practices.
As we now have concluded our presentation, we would like to take this opportunity and acknowledge our professors and the authors of the research. And please don't forget to like and comment and engage with us.